So what I want to do is walk through the concept of analysis of variance. And as you think about it, remember the big four questions. And the big four question number one that we're looking at here is, are these things different and how do you know? And what we use it for is to compute differences of means. Somewhere either in 610 or another course you calculated differences of two means using a t-test. And the problem then becomes, what happens if you have more than two things that you're comparing? And ANOVA helps you do that. You can use ANOVA with 3, 4, or 5 means effectively. Once you get into bigger pictures like that, you probably need to rethink how you're categorizing your data because it gets unwieldy and really difficult to interpret. I generally don't use ANOVA with more than 4 groups in most of my work, because once I get to a certain level of complexity, the results kind of get muddled. So just keep your models simple as you do this, and we'll talk a little bit more about that. All right, so let's talk a little bit about analysis of variance. You're using it when you compare more than 2 groups. And the test statistic is the F statistic. And we'll talk about what that is and how that works. But remember that for any particular test, statistical test, you have to have a test statistic. Later on, we'll deal with chi-squares. Like I mentioned before, you've done t-tests. There are different statistical tests that will matter for this. Even though I do ANOVA, I credit a lot of what I know about ANOVA to my wife, who is affectionately known by a lot of my students as the queen of ANOVA, because she's just really good at it. I'm good at it, she's really good at it. All right, so one of the things to think about, and this is a handy chart that I use in several of my classes to help you think about what question am I asking, and then also what kind of test do I need to run as a result. And for ANOVA, you are asking the question about, are there differences between groups? And you can ask the question whether or not you are testing people more than once. In this case, we're not. How many groups are you dealing with? If it were 2 groups, we'd be doing a t-test. More than 2 groups, we're going to do analysis of variance. And we're going to start talking about simple one-way analysis of variance, and I'm going to have you do a one-way analysis of variance so that you see it and you can see how it works. Think about this as your null, and always remember that the null says there is nothing happening here. There's nothing going on. Don't even pay attention. Don't worry. There's nothing behind the curtain, etc. There's no difference between these 3 things is really what the ANOVA says is its null. And the alternative is that there is a difference, and that if you find a difference, you'll base that on the F test. If you want to look at this conceptually, if you take 3 means, and what you're trying to do is you're trying to figure out, okay, what's the difference between mean 1, mean 2, and mean 3? If they come from the same distribution, you're going to have p is greater than 0.05, and there really is no difference between them. What ANOVA gets at is, if I take 3 means, I'm going to test them and I'm going to see whether or not these 3 means, when I lump them all together, are actually different from one another. And here's the thing, this distribution out here and this mean that we've taken here would indicate that if I take this as a group, they're not all the same, and my F is going to be above a certain level, and my p-value is going to be less than 0.05, and so that's really what you're really trying to test here. Now the F statistic, you should be thankful that you don't have to calculate it. When I was in grad school, we had to calculate this by hand. It's not easy and it's not nice. That's all I'll say. And given the size of the data sets that you're all working with, you might as well hang up finishing the calculation on your ANOVA until about June. Just so you know that. But what the F statistic is, it's a ratio, and it's a ratio between the mean squares between groups and the mean squares within groups. And you calculate all of those, etc. The ratio usually comes out to be a number greater than 0, and such as F equals 8.8. And you also sometimes write it indicating the number of your sample size and the number of groups that you have. And you do that as I've written it up here. I'm not that fussy about it, but I want to make sure you know that that is the case for a lot of people. All right. What I am really concerned with is that you do this. You tell me what the test statistic is, and then you tell me what the p-value is. So you'd say F equals 8.8, p is less than 0.05, or p equals whatever p equals. Don't just give me the p-value. If you just give me the p-value, I'll send it right back to you, because I need to know where you got the p-value. Did you do it from a chi-squared? Did you do it from an F-test? Did you do it from an R? Did you do it from a phi? In other words, what test did you use? And by telling me that it's an F-test, I know what you did. Now, obviously, I assigned the work. I have a guess of what you did. But if you're writing me a report, I don't know that. And so this is why you always do that. Examples of the null, there's no difference between the dependent variable. You'd say there is no difference between, workplace, salaries, and departments that people are working in. You'd say what the dependent variable is. The alternative is that there is a difference between those things, and so you write that out fairly specifically. Now, the F-test only tells you that a difference exists, right? And so it's like saying it's hot or it's cold. It doesn't say whether it's raining. It doesn't say whether it's, how hot. It doesn't say whether or not it's hotter than yesterday. It just says hot or cold. And so what you do is you have to do a bunch of follow-up pieces to be able to tell a better story. Just to remind you, these are the assumptions that ANOVA has, that you have a normal distribution, that your data is random, your variance is homogeneous, and that you've pretty much eliminated violating any assumptions of ANOVA, such as collinearity and things like that. All right. So one of the things that you get when you get an ANOVA output is a set of descriptive stats. And so you usually get the number of subjects in each one of your groups. You get the mean value. In this case, the mean is salaries. You get the standard deviation. And you get some confidence intervals for that, depending on how you ran the test. You also get the total of that group, and so just so you know that you get those as well. And if you ran the ANOVA, and this is a different ANOVA than the descriptive stats that I had up before, but let's say that I ran the ANOVA and I'm using state FIPS, so I've got 3 different states here, and I think I'm looking this one at age. And I'm looking at is there a difference in age between these 3 states? The null would be there is no difference in age between these 3 states. The alternative is that there is a difference between age in these 3 states. If I group them all together, F equals 5.4, P is less than 0.05, P is equals 0.004. I'd reject the null and I'd say, yeah, there is a difference between those pieces. The R squared here tells me that in this model I'm explaining 0.2% of the variations going on in age. So it's not a very good model. And that's one thing to note. It's not explaining a whole lot. The next thing you need to do is you need to think about post hoc tests. And what we do post hoc tests on is we do post hocs to begin to kind of say, all right, well, I found out these three things. If I lump them all into one box, that they're different. But if I took them out of the box in pairs, in all the possible pairs that I have, are those pairs different or not? And that's really what you're trying to do here. And so the threshold for this is 0.05. If you want a higher threshold, that's fine. 0.05 is generally how people look at this. So you'll be fine if you use 0.05 as your threshold. But here, human resources and research, are they different? And the mean difference is $88.09, and I think research makes more than human resources. So is that different significantly? Yes, it's less than 0.05, so that they really are different. The same thing is true for human resources and marketing. P is 0.01. Again, they're different. The third combination is research and marketing, and are they different? Here we have a difference. Here we have a result that's not the same as the previous two. What you have is P is 0.841. What that means is that there really is no difference between research and marketing. It's due to random chance. And as an example, what that does is that says I can really say there's a difference between human resources and research, human resources and marketing, but there really isn't a difference between research and marketing. It's a nuance that says, all right, the three are different, but pairwise, only 2 out of the 3 are different. There is a handy set of graphs that you do, and when you run these graphs, you begin to kind of get a sense that human resources is different than research or marketing. And so I like to run it with the error bars in the demo. I'll have you run it with the error bars just so you see that. All right. Next thing you want you to look at is effect size. And effect size is an important issue because what happens is that you may find significant results. My bet is that most of you will have data sets large enough that you'll find significant results. And when I was in grad school, that was enough, right? It's not enough. Because we have the availability of such large data sets, it's not uncommon to find significant results. And so we have to know whether or not those results hold any weight or not. Cohen has done a lot of research on effect size, and actually that's what Cohen is known for, is helping researchers understand whether or not the results are significant or not significant, are large or small effects. And so what you want to do is you want to make sure you run effect size. In the old days, I'd have you either run this and calculate this, or for a while there was a website, and the website still exists, that I would send you to and have you actually plug in your numbers. The nice thing is that SPSS now does this, which they only changed last year, so that's nice. There's not a lot of precision in this. So when I say small, medium, and large effect, that's really the case. So less than 0.02 is a small effect. Less than between that and 0.13 is a medium effect, and above that is a large effect. And so what I want you to do is I want you to kind of indicate whether you have a small, medium, or large effect. And so in doing that, that's all you need to say is whether it's a small, medium, or large effect. And so these are just cutoff numbers, and different places will report different numbers. Not to be upset about that, just so you know that can be the case. And so what happens here is it will calculate the partial eta squared, which is the number that you want to report. And so for this particular one, state FIPS 0.002, that would be a small effect. And so what we found is essentially a small effect. Now, don't be upset if it's a small effect. Don't be upset if it's a medium effect. I almost never get large effects. You simply report it as small, medium, and large, and that's all you do. So just so you know that. All right. So observed power. Observed power is the probability of making a type 2 error. If you remember that P is the probability that you're making a type 1 error, and if P equals 0.05, the probability that you're making a type 1 error, rejecting the null when the null is really true, is 5%. And so that number we have here, the observed power is exactly the opposite. And so the observed power is failing to reject the null when the null is false. The chart here is kind of handy for doing this. I actually prefer this. And I prefer this because it's a much more concrete example. And so the number that you want to use for this is 0.8. And so if it's 0.8 or above for observed power, you're safe from making a type 2 error. Type 1 errors are much more dangerous than type 2 errors. That's why there's a different standard. But know that you need to pay attention to both type 1 and type 2 errors. And if you make a type, if the probability for type 1 or type 2 error is too high, you report that and then you reject the null. All right. This is self-explanatory, I think, now, and what a type 1 and type 2 error might look like. All right. So next I want to talk about factoral ANOVAs, and I want to spend a little time with factoral ANOVAs. And, again, factoral ANOVAs is that you not only have more than two things, but you're dealing with more than one factor. And so you might be looking at both sex and the effect of an exercise program. So those are two factors. In the example that I do for factoral ANOVAs, I'm looking at sex and I'm looking at departments that people are in. In other places, you might want, if you're in marketing, you might look at the market segment and the cities that people live in and things like that. I mean, there are different ways to look at that. So there are different ways to design that. And you just think about it as, you're looking at males and females, and then you're looking at, which category are they in? Are they in the 5-hour, 10-hour, 20 hours per week category? And so it's categorical data, so it's not numeric. So you're lumping people into different boxes or different segments. When you interpret an ANOVA, what you're interpreting is both a main effect, two main effects, one for each factor is a main effect, and you also interpret an interaction effect. And it looks just like interpreting a one-way ANOVA, except that you have a second piece and a third piece, and it works just the same in terms of all of those, including effect size. So you get descriptives, and in this case, this is my example of salaries. You get males and females, and you also get the departments, and you get a total. This first line here for sex is a main effect. The code, which is really department, is your second main effect, and this is your interaction effect. And so for this example, F is 7.7, P is less than 0.05. You have, you would reject the null. Interestingly enough, you also now have power less than 0.8. So you might be making a type 2 error, and you need to report that. For your second main effect, which is department, P is 8.011, P is 0.001. Your observed power is 0.95. That would be okay. For this one, you don't have, for your interaction effect, you don't have significant results, and so you have no interaction between these two factors in how they're affecting each other. All right. In the post hocs, it's the same post hoc we did before. You don't have one for sex. If you had a third factor, you would have, let's say that the questionnaire said prefer not to answer, you'd have a third factor. Or if it listed out other options, you'd have a third factor. This is what the graph looks like, and so forth. So that's analysis of variance. You're going to build one on your own, and we'll see how that goes.